again to the let me say it again. Welcome once again to our webinar series on finding out the energy transition gap of Thailand and also the world. And throughout the seminars, we have heard from different speakers on different way we approach the energy transition, and we try to understand what are the mechanisms, how can we make it happen. And today we have a great pleasure to hear from Dr. Yeshui Zhang from the University of Aberdeen, who will talk about advanced metrology for study catalyst degradation and lithium-ion battery drying process. So yeah, without any further ado, I would like to invite Dr. Yeshui to give a presentation, and it will be a 45 minutes talk and then some 10 minutes Q&A. So for the audience, if you have any questions, please feel free to start typing them down in the comment section. And at the end, we'll pick some of the questions to ask our presenter. All right, thank you very much. And the floor is yours.
Thank you very much for your introduction. Good afternoon, everyone. My name is Yeshui Zhang. I'm a lecturer in chemical engineering based in University of Aberdeen in Scotland. I'm going to cover something I found is very interesting for my research. I'll start with a self-introduction. I did my undergraduate in University of Birmingham, my master in University of Sheffield, and a PhD at the University of Leeds. After that, since 2018, I worked as a postdoctoral research associate at University College London for 4 years at a time. Then I joined in University of Aberdeen School of Engineering as a lecturer. So where's Aberdeen? Aberdeen, we are based in very north of the Scotland. So we can actually see the northern light in winter time. And the first Nobel building, that's a place, that's our School of Engineering based in. And if you look at the new King's building, that's the oldest building in our campus. And we have a very nice of the library, so Duncan Rice Library. And I took this overview from our library. So where is Aberdeen and how convenient to travel to Aberdeen? I would like to invite all of you to visit Aberdeen in the near future. We are rather old of the university in the UK, founded in 1495 is rather old, and the fifth old of the university in the UK. We have 12 schools and covers almost all sorts of the disciplines. And we, as Europe's energy capital, the North Sea is just next to us. And for the transportation, it's very, very convenient. If you travel to London, it's only 1.5 hours of flight from London. And if you travel to Aberdeen, it's very easy to travel to us by train, 2.5 hours. And also we do have an airport as well. Now I'm going to start with some of my research. In general, I do the waste management. I am handling all sorts of the organic waste tears, plastics, biomass, crude glycerol from the biodiesel industry, and through the thermochemical conversion process, I do produce the carbon nanomaterials, for example, and the most of the time I would targeting on the hydrogen rich of the syngas. I do develop the process and also the reactor. Meanwhile, so one of my favorite parts of my research is to develop the in situ metrology to study the catalyst degradation and other sorts of the in situ metrology development. That's a main topic for today. And meanwhile, I do seek the applications for the products I produced from the waste feedstock, particularly for the multi-watt carbon nanotubes. I would try to use it as, for example, for the anode sides of the lithium-ion batteries or conductive additives for both sides of the lithium-ion batteries. The first subtopic about today's talk is how to convert the waste plastics or tears into the hydrogen and carbon nanotubes. Is one of the example. I have one of my collaborator helping me design this cover page for my reviewed article. So the whole idea is we want to collect all these waste material and convert it into these nanotubes. If you look at the two of these TM micrographs on the right-hand side. So one example is the same tear produced from the waste tears, and the other one is the same tear produced from waste plastics. What we can see is we have a rather of this homogeneous structure of these carbon nanotubes. I would say in general, we have done a lot of the preliminary research, and we confirm the quality. It's pretty close to the commercial of these multi-watt carbon nanotubes. The research relevant to this subtopic is funded by the Horizon Europe, is the European Union Horizon Europe program, and also the UKRI, which is a UK funder. And the whole idea for this hydrogen production from a waste project, the acronym is HEAVY. We are targeting to commercialize this project. Sorry. That's why we do not only look at the process optimization, and we do look at the potential economic benefits for commercializing this product, this process, and try to minimize the cost, for example, and the investment, and meanwhile to maximize the profits from this process to convert this problematic of this waste polymers into the high value products that's including the hydrogen and also the carbon nanotubes. As I just mentioned, I started this project since my PhD from 2014 at the University of Aberdeen. I have tried all sorts of the processes, optimization, that's including all parameters and material development for the catalyst design, and also the modification of the reactor. So I'm not going to go to the details, and all of this work have been published. If you're interested, you could go through the details of this process optimization results. So what I can confirm is we can definitely produce the high quality of the carbon nanotubes. Meanwhile, we can try to maximize the syngas, the hydrogen-rich syngas production at the same process. And one of the challenges for commercializing this project will be the carbon nanotubes growth mechanism. Why? Is that in general, through the thermochemical conversion process, so we have to use the catalyst, and the carbon deposition on the surface of the catalyst is one of the major issues to degrade the catalyst. So that will suggest all of the researchers to try to either develop one type of the catalyst that can resistant to the carbon formation. And the other way is to understand how this carbon was formed on the catalyst. And meanwhile, we can convert this problematic of this carbon into the high value of the carbon nanotubes. That was my aim. So I would try to investigate the synthetic growth mechanism from this process and to see how this carbon nanotubes forms. Why sometimes we can produce the, if you look at this figure of the B on the left-hand side, we have this solid structure of these carbon nanofibers rather than the hollow structure of these carbon nanotubes. And in the worst case, we even have the amorphous carbon formed on the catalyst surface that it will only degrade the catalyst without any of the values, I mean the profits for producing the amorphous carbon. So I want to find out the synthetic growth mechanism. In that case, I could really control the process and maximize the production of the synthesis and also try to increase the quality. Obviously, we want the synthesis to be formed more homogeneous. And right-hand side in journal, we do use a Raman spectroscopy to confirm the quality of the CNT produced from this process. And I'm sure some of you have been using the Raman spectroscopy. It's very powerful of the equipment to help us to identify the amorphous carbon and graphitic carbon from the mixture of these samples. And we do use a scanning electron microscopy, like the figure E here, and the transmission electron microscopy to confirm the production and the quality of the CNTs we produce. And regarding the latest research on the CNT growth mechanism, as I mentioned, this is one of the most challenges. I have been discussed this case in my reviewed article. So we have to use the most advanced of this in situ instrument, or alternatively, we can develop this in situ metrology to help us to understand the mechanism. Why? Because this is a dynamic process. To form these carbon nanotubes on the catalyst surface, it can happen like immediately, as long as the carbon atoms being released from the with the plastics reached to the catalyst support. If you look at this size of the TEM images was captured by using the in situ TEM early this year at the diamond light source, that's a synchrotron source based facilities. And what we captured, everything happened with within a minute, even less. And what we try to simulate, not really simulate, we mount the catalyst powders and the plastic powders in the capillary tube, and we do have the heating stage. And meanwhile, we do use the fast capturing function of this in situ TEM to capture this particle. So that is a catalyst particle, and on the surface, you could see first the image we captured, we can really see the carbon atoms being formed on the surface of this catalyst particle. And later on, you can see this layer has been growing up. And later from the figure C over here, you start seeing some structure of these hollow carbon nanotubes. And this tube being extended in such a way until we can see the length. The diameter has been fixed because based on the published work, the diameter of these carbon nanotubes will be dominated by the size of this catalyst particle, and the length. If you see the length between this top layer of this tube and the bottom has been extended. Well, that's some of the latest finding we haven't published yet, but from my personal point of view, I would say this is really something amazing. I was so surprised. I have been working on this project for 10 years or even more than 10 years, but this is really something not being overcome yet. I'm still working on this to try to capture more of these images to see a longer size of these carbon nanotubes to confirm and propose the latest of this CNT growth mechanism with the plastics. Because since the last 10 or 20 years, all of the researchers we refer to the published of the CNT growth mechanism, that is either is a tape growth mechanism or based growth mechanism for the chemical vapor deposition method to produce the carbon nanotubes from the pure methane. But for producing these synthesis from waste precursors, that is too complex. We have tens or hundreds of the hydrocarbons being produced through the thermochemical conversion process of the waste plastics. So the CNT growth mechanism from this process can be very, very complex. And as I just mentioned, I still want to find out the applications of the CNT I produced from this process. So one of the try I have done is to replace the anode side of the lithium-ion batteries. So if you look at the structure, or in general, we have the cathode side and anode side, and nowadays the anode side was using the commercial of the graphite as an energy storage material, and it's pretty much similar as the carbon nanotube. So that is one reason I want to replace this commercial graphite, and depends on the country. For example, UK import lots of graphite from China or America. So we have to find out an alternative sources of this anode material. That is one of the reasons I'm doing this work. So this is a macro structure. Of course, it's a model structure of this anode side. The pink particles represent to the active material. For example, the commercial of this graphite, and the yellow straps here, that's a bender, and it's more like a blue. We try to connect all of these particles together. And if you look at the small black dots here, that's a conductive addictive, which has been normally mixed with this electron materials to try to boost the electrical conductivity of this electron material. And for the commercial lithium batteries, we're using the carbon 45 or carbon 65. That's a specific surface area of this carbon material. And all of this green stuff here, that is the solvent, because this model represents a drying process of this electrode manufacturing process. And at the bottom of here is a current collector for this piece of the electrode. Well, this results, the electrochemical performance of the CNT have been used to replace the graphite for the anode side of the lithium battery, have been done and also have been published by this work with one of my visiting PhD students. I would say in general, the performance of this CNT is quite close to the commercial of the graphite. That is the indicator for us, and also the encouragement for us to carry on the work to use this CNT produced from waste precursors as an active material for the anode side of these lithium batteries. More of the details you could find it from this paper we published last year or year before. Another subtopic is relevant to the advanced metrology for studying the catalyst degradation. We have a nice of this cover page been published to the Chemical Engineering Journal 2-3 years before. And this specific metrology will be the X-ray nanocomputer tomography. I will tell you why I want to use this one. So this size of the data is the conventional of this scanning electron microscopy micrographs. It's powerful and very useful of this technique. We can see the surface of this catalyst particle, and this piece of work I was using this fluid catalytic cracking catalyst, and this type of the catalyst is normally used for the oil refinery industry, and with the particle size between 50 to 200 microns something. It's rather homogeneous. And if you look at the pristine of this FCC catalyst, it's kind of rough, but it's at least the shape is quite homogeneous. And I tried to simulate the degradation process of this FCC catalyst in through the small chemical conversion process. And you look at the surface of the catalyst particle, you start seeing some of the defects, and there's something being formed, or it's just the surface of this catalyst that been damaged by the thermal process, or this peeled of this surface. It's powerful by using this SEM, okay, see the surface, but we want to identify the internal structural change of this catalyst particle. And this FCC catalyst and other types of these heterogeneous of the catalyst that we use are porous structure inside. So you still want to find out what happened inside, if the porous structure been damaged or anything will go inside of these pores to change the porosity or surface area. That is one of the powerful functions by using this X-ray nanocity. So if you look at this, for example, this figure A on the left here, So that is one of the cross-section of this single FCC catalyst particle. Instead of looking at the surface, we do look at the cross-section. And even we can reconstruct this 3D structure of this single catalyst particle and doing the first analysis. So we have published 2 pieces of the work by using this X-ray nano-CT to see the internal structure revolution of this FCC catalyst particle. So the right-hand side is another piece of the work. So we do not only look visually see the internal structure change. We are doing the research is that we need some kind of the quantitative results. That's another powerful functions. What we can do, we scan the particles and with more than thousands of the tomograms, I mean the cross sections, and then we use the software to reconstruct the 3D structure. And furthermore, we can segment the different components. For this FCC catalyst, we can segment the main structure of this catalyst is the clay, and also there's quite a lot of the pores inside. That is the design, the feature of this FCC catalyst. And another component will be the zeolite that plays a catalysis role in this process. And if you look at this one of these figure here, that is actually telling you the distributions of these 3 segmented components for one of these FCC catalyst particle. And the x-axis here is 0, indicates the center of the FCC catalyst particle, and the 25 that is the actual of this FCC catalyst particle. So what we can see is the main structure of this catalyst, the clay, and it's almost homogeneous throughout the catalyst particle, but at the surface, you can see more of the pores. I think that makes sense because it's pristine and fresh of this catalyst. We haven't used it at all, and more of the open pores at the surface. And meanwhile, if you look at the red area in this figure, that is the homogeneous distributions of the zeolite throughout this particle. And the rest of the figures here are the different degraded stages of this catalyst. So what we can summarize, you can see the surface being blocked either by the clay or some of the other materials being formed at the surface to block the surface pores. That's why less of the open pores at the surface of the particle. But there is no change for the zeolite distribution. That's one of the key findings for this piece of work. And the right-hand side figure is another continuous work for this study. Except of these different contributions of the composition, so we can also segment the size distributions for one type of the component. For example, is the zeolite, because it provides acidities of this FCC catalyst to catalyze the process. That's why we want to find out more information about this zeolite distribution. But so if you look at these color maps, the different color represent to the different size of these zeolite fragments throughout this single FCC catalyst particle. We do have the random sizes of this zeolite fragment, and also we can quantify the distributions of this zeolite distributions throughout one particle. So that's actual of the quantitative result we can extract from this X-ray nano CT. What else we can do with this X-ray CT results is the process distribution. Well, it's quite normal for the researcher who are working on the catalysis. We normally use a nitrogen absorption and desorption method to quantify the process distribution. But that is for the batch analysis. But we're using this X-ray CTs only look at a single catalyst particle. We can still count how many of the pores in different sizes and plot these process distributions. Of course, by looking at one catalyst particle, you might ask me how am I going to confirm the results are reliable? Yes, I'm still doing the batch analysis, use a conventional analytical method. confirm the porosity, pore size, and also pore size distributions, pore volumes for the batch of these FCC catalysts. That's a result. So we can confirm our X3CT results are rather reliable. I'm not going to repeat this conclusion. If you're interested, there are 2 publications, so you could look at the details from the references. And that's 2 of the graphical abstract for the publications. And except of highlighting our findings, I still point out the research gaps. That's something we still find out. For example, the surface, the pudor surface of this catalyst. For now, we can confirm it could be the damage of this clay structure, it being clamped at a high temperature, or it was some of the carbon being deposited at the surface. We will need more of the synchrotron science-based facilities to help us to identify the chemistries of this pudor surface. Another subtopic for my talk is about the advanced metrology development for studying the lithium-ion battery drying process. I have made this module to simulate. This is a very, very simple process to dry the electrode. We mix the slurry at the beginning, and then we try to evaporate and remove the solvent to make a compact and homogeneous distribution of this electrode on top of this current collector that's in silver color here. Well, everyone was thinking it's a very, very simple process. But actually, I was actually having the same question at the beginning. I'm working on this project, but later on, I found more things, so we are not sure. And for the drying process, well, in general, this is a lab-based of this process to manufacturing the lithium-ion batteries. We start with making the electrode, and then, cut the electrode into different style, different shapes. It depends on the types of the batteries you want to make, and then doing the formation and the condition stuff. And even for the commercial process is it's quite similar. It just the equipment used are different. As I just mentioned, I had the same question. Drying process, it seems like and sounds like only the physical evaporation of the process involved, and nothing difficult is there. That's why I did a very comprehensive review and summarize what parameters or the variables would be involved in the drying process for making this lithium-ion battery electrodes, and how these different parameters will affect the performance of the electrode. For example, if you dry it very fast, and this drying rate can be affected by temperature, radiation, intensity, pressure, whatever, depends on the type of the drying method you want to use. And this will lead to the different types of the defects for these electrodes, and then this will finally affect the electrical, mechanical microstructures of these lithium-ion batteries you make. And more details you can find from this review article. I have these models maybe more easier to explain the different defects. For example, we just discussed the different compositions of this electrode. We have the pink particles as the active materials. We have the solvent. We have the dark dots, the black dots represent conductive additives, and also we have the yellow straps here, that's a bender. So if we are drying it too fast, this component, if the process is too slow, we could have this component sedimentation. Ideally, we want this everything to be distributed like homogeneously, but if you dry it too slow, we cannot reach to the homogeneous structure. And if you dry it too fast, the bender will be driving, because the solvent will be evaporated, and this will drive off the benders to the top layer of this electrode or this coating. And in that case, you move all of these benders to the top, less of the bender at the interface between the current collector and the coating. So you have the delamination of this coating and other types of the defects. And that is another highlight from my reviewed articles to see what type of the metrology we can use to help us to understand the different drawing stages and to understand the drawing mechanisms. And in that case, we want to control the drawing process. Of course, I have tried everything, like the previous slides. I have covered just too many of the characterization methods. I have tried the most of them to see what kind of useful information. For example, using the X-ray CT. This is not actually nano CT, it's actually micro CT to help me to see the 3D structure of the electrodes and also see the composition distributions of this electrode layer and the thickness of the layers throughout the drawing, for example. And also other type of the characterization. I will try to see the adhesion force between the electrode coating and the current collector, some of the results, and also the FIB SEM. I was using to try to see the because the SEM is here of the resolution comparing with X-ray CT, so we can see more microstructure and of this electrode materials that we made, so we can see how this drawing temperature will affect the component distributions of the electrode throughout the layer. And well, of course, all of these electrodes I made at different temperatures, or in the other way, we can see how this drawing speed will control the quality of this electrode. I have tried confirm the electrochemical performance of these cells. I made all of these electrode with coin cells and tested the electrochemical performances, and well, the result is rather clear for us. If you join too fast, of course, the capacity will be reduced and the cycling capacity will be reduced as well. As a conclusion from the 2 or 3 of my papers, so I'm going to skip this slide. And the last topic of my talk is another institute I developed to see the dynamic of this electron drawing process. This is 2 diagrams also from my reviewed paper. So I summarized the advanced metrology we can use to see to help us gain more of the information about the electrodes and try to investigate the performance of the electrode being affected by the different drawing process. But what else is my aim is really to see something happen immediately, the dynamics of the change, rather than doing the executive characterization. So that's not really something I'm interested in. So I have grouped all of the metrology I have been reviewed and grouped them. It depends on the capability for analyzing the materials or the electrodes or the battery cells. And also I have grouped them in a different way to see if this equipment, for example, if it's AFM, is capable to do the in situ experiment to help us to identify the dynamic information of the drawing process or not. Or some of the methods have been used in other fields, but not yet in the lithium-ion battery field, but still is a potential we can develop it and use as an in situ tool to help us to identify the dynamics of the electron drawing process. So that's the result. After doing that, it's very, very clear for me. So I have reviewed this list of the different methods in my head, what I can use to help me carry out this study. And also I have tried them, and after trying them, and I have also identified the capability of the different metrology. So there's a gap, definitely a gap. We need something with a very simple of the design and provide us a very fast of the results or the reading to indicate if the drawing is too fast or too slow. We can adjust its meanwhile to reduce the waste or reduce any eliminate any of the defects for drawing these electrodes. So this is the acoustic tool I developed This is actually a second generation. So the method, the principle is very, very simple. It's just based on the responsive mode of these the acoustic signals, and we use the same of the transducer image and receiving these signals. And this change of the signals provides me the different informations between the interfaces. For example, the drawing is we have several different types of the interfaces. It's a solid and the liquid. The solvent is a liquid, and this active particle is solid. So the number 4 interface is solid and liquid interface. And also there's a current collector CC, and between the solvent is another type of the solid and liquid of the interface. And if you have this active particle, like the number 5 of this interface, particle between the CC, that is the solid and solid interface. So by interpreting the received of the acoustic signals, so we can tell the stories of the drawing, and in that case, we can really adjust the drawing process. And well, the tool itself is provides us rather fast of the reading. But for interpreting the results, so we need lots of the baseline investigations. I'm going to skip this. And in general, what we can do, this is a best graphical abstract alike. So we, by using my in-situ acoustic tool, we could have captured this color map immediately within, well, less a few minutes. We can have one of this color map, and it tells us the different drawing stage. And by interpreting it using the coding I designed, I could really read the drawing stages of these electrodes. Therefore, we can see this drawing is too fast, and we can change the setting of the drawing immediately to control the drawing process to try to optimize this, rather than we joined and waste a lot of raw materials and then go back again to optimize the process. We can eliminate all sorts of this waste and optimize the drawing process. That's the end of my research talk. And thanks for all my founders and collaborators. And I still want to spend a couple of minutes to introduce one of our new Elsewhere and IKME journal. We just celebrated 3 years birthday in summertime, and we have our first impact factor is 10.2. The journal title is Carbon Capture Science and Technology. Well, we have been growing very fast in last 3 years time, and still for this year, the APC is being waived until end of year for 2 of the special issue. If you have any of the manuscripts, you haven't really find the home for them, please, I would recommend you to submit it to our CCICT journal. We do run the annual conferences pure online. Last year, sorry, well, still 2024. Well, CCICT 2024 conference was hosted by Professor Chula and other researchers from US, and the editor-in-chief for CCICT journal is Professor Chunfei Wu from Queen's University of Belfast. I'm the associate social media editor and one of the associate editor. So if you want to engage with us for any kinds of things, submissions or participating in our conferences, or even if you want to host any of the CCICT annual conference, do let me know. Or if you have your publications want to be disseminated through our platforms, you can reach to me as well. We are running all these social media accounts, try to disseminate the work. Another thing, and is the last thing, is Professor Andrew Musk from University of Edinburgh and myself, we are going to host the 26th International Symposium on Analytical and Applied Pyrolysis 2028, based in Scotland. And still plenty of time for you to think about and make your plan to visit Scotland. So I took this, I never really steal the image from Google Images. I took all of this image by myself. It's a really nice place, the Donata Castle, uh, based in Stockholm. Is a small town just next to Aberdeen. So I would like to welcome everyone. And the last one is a slide. I don't know if we have enough time. If I have spent all the time, we can skip this video. Uh,
No. Let's watch it. Let's watch it.
all right. Okay. I think it's a nice video. That's all of the nice views in Scotland. Scotland, we do have the nice whiskey here.
Mm.
That's a Donata Castle. We just seen the image.
Wow. The golf course are amazing. I remember
Sorry?
the golf course. Oh, yeah.
If you do love golf, Aberdeen is the best place to visit as well. It's a Northern Lights. That's it. I would like to invite all of you to come to Scotland. Of course, Thailand is a beautiful country. I have been to Thailand a few years before, but Aberdeen is a very, very different.
All right. Thank you very much, Professor Yeshui, for your great talk and very inspiring. Especially, I was intrigued by all the techniques that you have used, like X-ray, CT, the in situ, TEM, ultrasonic, like all these different methods that, I never thought of that is useful for characterization of, something like batteries that really need good characterization so then we know what is going on. So yeah, really good, great talk. And now it's time for Q&A. But before that, can I tell a little bit about our webinar? So Chula Next Energy webinar is sponsored by the Royal Academy of Engineering under the program called Frontier Champions. And we are running a series of webinar, and this is our sixth already. And we have this almost every Friday. So if you're interested, you can, if you're interested to hear our past talk, you can go to YouTube video and search Chula Next Energy, and you can find all the past talk over there. All right, now it's time for Q&A. I think we have one question now. Professor, would you like to read it and answer the questions? Can you see the question?
Yes. How does the synth and other component contribute capacity of the graphite? Well, actually, the synths I used is to replace. I mean, I didn't use any of the graphite. Basically, the synth was replacing all of the graphite in the anode side. Why the capacity of this synth is higher than the pristine graphite? Because the synth is more porous than the graphite. And also because of the structure is thinner of the tubes itself and provides hair of the electroconductivity. That is one of the features of the carbon nanotubes. That's why it will boost the capacity of the lithium-ion batteries.
Okay, do we have more questions from the audience? I think at least 3-4 has left.
It's okay if you don't really have any questions. I know that's a lot of work because I have been working as a postdoc for 4 years. I think it's quite long for some of the researchers. That's why I have been involved in several of the different projects. And if you have all of the reference, you can go back to the recording to see if first of the questions, you can reach to me by email. I'll be more than happy to answer your questions through emails, or we can arrange the Teams chat for answer your questions. Of course, I'm open for all sorts of the collaborations as well. For the students, if you want to visit us as a visiting students, and for the academics, if you want to collaborate with any of my existing projects, or we can propose some of the new projects, just reach to me. I'm open to everything.
Yeah, that's exactly what I wanted to ask. Whether is there any specific area that you are looking for collaborator, or like if you think about Thailand, maybe we deal with a lot of biomass, and you talk about biomass conversion from the early on into carbon nanotubes and so on. Yeah, if you have anything, like, do you have anything specific in mind that maybe our community can reach out to you and someone who work on those topics?
Well, yeah, biomass for doing the thermochemical conversion of the biomass in Thailand, I think can be one of the thing we can work on together. Well, because I know biomass is got a lot of the quantities in Thailand, similar situation in China. But I mean, it depends. It depends on your research interest as well, and other academics' research interest. I'm like a kind of doing everything. Covering the thermochemical conversion and the catalysis, heterogeneous catalysis, and also the energy storage. So quite broad of my research interest. Anything you want to work on together, just let me know.
Sounds great. Thank you very much. So I guess, okay, thank you from Annie, Professor Anongna, the leader of this project. And yeah, with no more questions, I would like to thank Professor once again for your time early on in the morning. And yeah, this video will be uploaded and people can always go back and watch it. Yeah, anyway, thank you very much.
Thank you. Enjoy the rest of the day.
Thank you.
Okay, bye now.
Bye-bye.